This is Bobak Bike, Professor Seedrobe here. Once again, Intro to Meteorology, Lesson 4. I have to say this. I said this in the last ones. Remember that all the images in this presentation are not my own, nor the style or format of the lecture. Under fair use is this brought to you. Um, I'm not going to read all that, okay? But basically, to my knowledge of the extent of the law, I can provide this to you. All the words are my own, but like I said, the format and some of the images may not be. If you have any issue with this, please contact this email address. All right. So when we're looking at this, sorry, that's kind of, the text wasn't supposed to be there. That's supposed to come on later. But basically, we know the water cycle, right? We know we have evaporation, condensation, precipitation. You learned that in elementary school, right? Well, I this slide is just basically, it's supposed to be kind of like review, but we also have some things that we just need to know. And if the water is warmer, we're going to have more evaporation. Doesn't that kind of make sense? At a fundamental level, it should. And then advection, in case you don't know what that is, that's just a process of moving moisture. And precipitation, although it occurs a lot, is actually pretty hard to get it to occur mathematically. We're going to talk more about precipitation in the next video, but we're actually going to talk mostly about humidity in this one. Humidity, you might just be like, whatever, humid, it feels not good, whatever you might say about it. Well, humidity is very important, relating to a lot of things, and we'll figure out why. So, what even is it? It is the amount of water vapor present, but it's kind of a loose term because we have different ways of measuring it. We have absolute and relative humidity. Absolute humidity is the actual, that's what absolute means, measurement of the water vapor, grams per meter squared. Um, Temperature does not change this. And that's the point. Like, if it's absolute, that's why temperature doesn't change it. Because if a different factor changes it, that makes it relative. In case you don't know the difference between relative and absolute. Like, I can say, I am 7 miles relative to whatever, like, or I can say where I am exactly. That's what we're talking about here. So absolute isn't actually really what we look at usually. We have specific humidity, which is a form, it is an absolute measurement of humidity. But what we look at more is actually relative humidity, which is a ratio. And the reason why is because it's just one of those things where, there's confounding variables. If we don't think about how temperature changes, we're going to find out that temperature does affect relative humidity. If we don't take that into account, it's not really useful for us making, general observations, if that makes sense. Um, Relative humidity is the actual water content divided by the potential. So that's the key thing here. It's not just the actual water content. We're also saying as a ratio, compared to the what it could be. And what it could be is depending on what the temperature is. Does relative humidity tell us how it feels? No, actually. So that's a common misconception. A lot of people will think that, you know, whatever the relative humidity is, which is a percentage, that's how we usually display it, not a decimal. Um, we're going to say, oh, all right, 99%. So it feels so sticky out there. That's a kind of bad thing to say. It's a common misconception. We're going to actually find out that dew point is what's going to tell us more about how it feels. Um, let's just talk about mixing ratio. The mixing The mixing ratio is the amount of water vapor relative to mass. So once again, this we're talking about water vapor relative to mass, but this is not affected by temperature. It's not dependent on anything. So this is also an absolute measurement. And you might say, oh, it's dependent on mass. Well, that's kind of just given. That's not what we're talking about. We're saying it doesn't change because of like, for example, temperature. Um, and what this is the mass of water vapor divided by mass of dry air. So we're saying the mass of the water vapor divided by just the dry. So um, let's look at this graph to kind of get a better understanding about what happens with mixing ratio. So we'll see over here, we have mixing ratio on the x-axis. We have height above the surface on the y-axis. We can see that as mixed, this is the way that we want to look at this is not as mixing ratio increases. We're going to just think about as height increases. So as height goes up, the mixing ratio goes down. So that can be a little bit tricky looking at it this way. It's almost like reverse because usually we'll look at this and see what this does. And you could do that. You could say as the mixing ratio increases, height decreases, but that doesn't make sense, right? Because um honestly to me this graph's like almost backwards, but they put it this way just because they think height is better on the x or y-axis. But you can see that over here, where there's a higher height, there's a lower mixing ratio. So that's just what's important. We can see also depending on, what uh, type of area we're in, climate, that can change too. Vapor pressure. Vapor pressure is simply the amount of atmospheric pressure exerted when by water molecules. Simply the movement of molecules exerts a vapor pressure. This is also an absolute measurement, and as you might guess, since it's a pressure, we measure this in millibars. Evaporation, you probably know what it is, but in case you don't want to know the, specific definition, this is talking about when we're changing from a liquid to water vapor, and water vapor is a gas. So liquid to gas, um, we're thinking about that. If there's evaporation, you might think of, okay, we have a lake, ocean, the water is going up and changing into gas, right? And remember, based on our last lecture, I think it was the last one, this is actually a cooling process, which might seem kind of confusing, but that's just the way that it works. And if you need a review on that, please watch the other one. But this is actually considered a cooling process. Um, Condensation is when we go from water vapor back to liquid, right? Um, and technically, we'll look more at precipitation, but we could actually, if there's ice accumulation, that's a solid, right? But this, when we have condensation, that's when we get clouds and precipitation. What is saturation? Saturation means the max water vapor possible at a given temperature. And basically, that doesn't make sense, look at this. If we're unsaturated, then the amount of evaporation exceeds that of condensation, right? But if they're equal, then this is when we have saturation. And what actually happens when we have saturation? That's when we get clouds. So that's why this is important. This is only when we can get clouds, is when we're saturated. So if the amount of evaporation equals that of condensation, we can get clouds. And that's how we can, get precipitation, storms, severe weather, whatever it may be. Um, there are three saturation values you need to know. There is saturation vapor pressure, saturation specific humidity, and saturation mixing ratio. We already talked about what those things were. But the main thing that I'm trying to say for the slide is as temperature increases, all of these do. So they're dependent on temperature and they have a positive correlation. So if we have a higher temperature, we're going to have a higher saturation, vapor pressure, specific humidity, and mixing ratio. Saturation changing with temperature, it's not linear. And what did I just say? It increases with temperature, right? As this is what you can see, right? And well, this is vapor pressure specifically, but then we also have specific humidity. And what did I say? we can see as temperature increases, they both do. And it's not linear either, right? It's not a straight line. It's like, ooh, and then it goes up almost exponentially. All right, relative humidity. We already talked about this some, but now I'm going to get into more detail about how we would calculate it, right? Remember, the actual, this is the actual moisture divided by the potential. So if we're only talking about the actual moisture, that's called absolute humidity, remember? So that's not, remember I said that's not helpful always because it doesn't really tell us as much, but because this is dependent on temperature. So look at what I have here. The higher the temperature, the higher the SHH. What is that? Saturated specific humidity. And what does that mean? That means the potential, that's the possible moisture that we could have. So a good way to explain this is let's just say, okay, you can think of any container. So let's just say I have a water bottle. Um, that's not a good water bottle, really, but the size of the water bottle is what we would consider the SHH. The amount of water in it would be the SH. So what is there actually divided by how much it is? So if our water bottle is halfway full, we would say 50%, right? Um, and so that's what we're saying. If we had if the ratio between these like I don't want to just throw out some random numbers, but if the SHH was two times as much as the SH, so that would mean it's only halfway to what it could be. That's our relative humidity. So that's how it works. So SH, what is there actually there? SHH, how much could it be? And when they equal each other, that's when there is saturation. That's when we can get clouds. And remember, I said this won't tell us how it feels. It tells us how close we are to saturation and getting clouds, right? Um, so if we have a higher temperature, then there's a higher SHH. So let's say um, we had 50% relative humidity and the temperature goes up. What does that mean? What's going to happen to the relative humidity, assuming that the SH stays the same? If we have a greater denominator, that results in a smaller number. So this would be bigger because the temperature goes up. So maybe it goes down to 47. So that's how it works. Higher the temperature, the smaller the RH will be, only if, of course, the specific humidity stays the same. Oh, I was about to turn off the recording and I meant to, what I was trying to do is erase this. And that didn't work. Forgot how to do that. Okay. Um, so what does this mean? Let's just see this video for a second. Okay, so whatever. You might not know what that is means, and that doesn't matter. But what do you see in the background? That's fog, right? Uh, fog, we have fog. That means that relative humidity is 100%. That's as simple as it is because that's a cloud, but it's like a cloud on the ground. That's what fog pretty much is, right? So that can tell you why it's important because fog is dangerous when it comes to roads. So yeah. All right, let's look at this for a second. What do we see here? Um, oh shoot. This is what we would call like a diurnal representation. Diurnal means kind of fluctuating through the day. We can see what happens to temperature. We know that temperature is lowest around like 6 a.m. or something, right before sunrise. And it's highest not actually at noon. It's highest closer to when the sun goes down. But what happens to relative humidity? We see it's almost opposite. And that's what I was saying on the other slide. If we remember what it is, we have SH divided by SHH. SH being the what we have, SHH what we could have, what moisture we could have. When the temperature goes up, this goes up. So let you know, like if we have one half, that is bigger than one third. So the bigger the number on the numerator, that makes it a smaller number. So if this goes up, we know that RH has to go down because the bigger denominator means the actual thing will be smaller. So that makes sense of why we know temperature makes this bigger, which is why this would end up smaller. So that's why when temperature is higher, this is lower, and when temperature is lower, this is higher. That's what we're saying. And um, we're actually going to have a higher relative humidity in the mornings sometimes. And that's what I'm talking about, how you can't say this tells you how it feels because we're not going to really say it feels humid in the morning usually. But what might tell us that? That's dew point temperature. Well, the dew point is basically how much the air needs to cool for saturation. So it's saying the temp it can be displayed in the temperature. So if we have a dew point of, we could just say I already put it over here, 60 degrees. And the actual temperature is 65. That means we got 5 degrees to go for 100% relative humidity or saturation. And the higher this is, the more bleh we would say it is. So we have, like I said, 60%, not 60%, sorry, 60-degree Fahrenheit dew point. That's going to feel a lot ickier than if we had, let's say, 32. So the higher the dew point temperature, this is where it starts to feel worse outside, to people that don't like humidity or the feeling of humidity. So that's where it can get kind of confusing, right? Because it's almost like opposite of what you've been almost trained to think. But what is a dew point depression? This is the temperature minus the dew point. So in the example we just had, we had 65 minus 60. Can't really see that, but that is 5-degree dew point depression. And if we have a higher dew point depression, we have less clouds, lower, more clouds. So this is small. So it's gonna be, pretty cloudy possibly. And if we got up to like 64 dew point and the temperature is 65, okay, we're getting some clouds. And then if they're the same, that is saturation. So we definitely have a lot of clouds going on there. Uh, let's see here. How do we measure humidity? So the main, ometer is kind of usually the suffix of things that measure stuff, but hygrometer, that's what we use to measure humidity. There are different types, there's actually a hair hygrometer that you can use because as we know, a human hair can actually react to humidity, right? Because it might be like this, but then it might get like frizzy if it's humid, right? Uh, okay. How can we reach saturation? So first of all, you might be wondering, why would we even care about that? Well, when there's saturation, that's where we're going to get weather that's of any interest, right? I mean, no saturation, we got blue skies, and we're like not super interesting. But when we have saturation, we have the potential for T storms, right? Other weather that's interesting. So what we can do is we can increase the water vapor. What would that mean? That means our SH is going up. Or not, sorry, not going up. It's getting closer to the SHH. So we're saying we're making what we have closer to the max of what it could be, meaning this gets closer to 100%. And if that is 100%, then what do you know? We have saturation. So that's why. And then we can also change the temperature of a mass. And if we mix cool air with warm, is how that can happen. All right, so the last thing that we're going to look at in this video, this last slide right here, um, dew points with seasons. So what do we see here? So let's remember what this is, okay? I'm looking right here at the Fahrenheit. The number that's in here, this is the dew point temperature. So we don't know what the actual temperatures are here, but we know that the difference between them, if it's smaller, that means that we're closer to saturation. If it's bigger, we're far from it. But wouldn't this make sense, right? What might we expect the temperature to be? Let's just say uh, anywhere. How about right here, Ohio? Okay, well we see it's about 20 dew point temperature. Well, in January, it probably could be it could vary, but let's just say maybe it's at this point in time 30. So we have 10 degrees to go to get to saturation, right? And the only places where it might be a little bit, we have a higher dew point temperature is here. And this is actually going to equate to how it feels. So it's not going to at all feel humid here. It might actually feel a little humid right there. And then let's look at how different it is in July. Well, heck yes, it's always humid here. I don't if you've ever been to that area in July, you would know. Even this brown right here, very humid as well. What about right here? Why would this be blue? Well, we have some mountains right here, Rocky Mountains, and that actually is very important. How come? It's almost like a barrier. And so we have a lot of water vapor that builds up right in these Great Plains. Now let's think about what that would mean, right? Okay, so first of all, let's look right here and see what the dew point is. We have a dew point of 60. So that in some places, I'm obviously not the same everywhere, but um that means that obviously it's going to feel more humid and it could be really hot there, right? But we're going to have a lot of water vapor buildup. And that is the reason why we have the most severe weather right there. So that's actually all I have to say in this video. Um, but we can start to see these pieces coming into play of how this stuff matters for what's probably, in my opinion, the most important things for weather, like severe weather and impactful weather. We want to understand why it happens, and this is just kind of the foundation.